Good afternoon, everyone. It is Saturday, March 30th, and this is a little mini lecture on drag. Um, when we drop extended objects from a certain height, they are going to ultimately meet with resistance due to the fact that they're falling through a fluid, i.e., air. So we're going to analyze this motion, and we're going to try and come up with a model as to how the filters will fall with time, and we're going to use coffee filters for this. So I have on screen here a Mathematica document that describes the physical situation that's happening here. So you look at the coffee filter. The coffee filter is represented as a dot in the particle method, and you have two forces acting when we consider air resistance. The gravity is acting downward. That's an obvious one. But what is not obvious and what sometimes can be cause trouble in analysis is this air resistance force, which can be either proportional to the velocity or proportional to the square of the velocity. So I've written these two expressions here in my free body diagram. Now, using Newton's laws, the sum of the forces equals to mass times acceleration, I have one of two choices. If the object is falling and the air resistance is proportional to the velocity, then I have the first expression up here, mg minus bv equals ma. If, on the other hand, and this is especially true for extended objects, that the air resistance is proportional to the square of the velocity, then the equation we have to solve is mg minus cv squared is equal to ma. So, how are we going to solve this? In the algebra-based class, which we are in, the answer is we're not. We can't really solve this because of the fact that the acceleration and the velocity are both derivatives. We would need the mathematics of differential equations to do it. In the calculus-based class, I would have you guys do the solution, and I would show it to you by hand as to how it's done, but I'm going to leave that alone for the time being. In the event that the particle reaches what is called terminal velocity, where the weight of the object is balanced by the resistive force, then I have the sum of the forces is equal, net force is equal to zero, and I can actually solve this equation. As you can see, I did it for both linear velocity, mg minus bv equals zero, and the terminal velocity is dependent upon the mass, gravity, and this coefficient b, which is called the drag coefficient. Now, b is the standard representation for the drag coefficient for the velocity, for the air resistance proportional to the velocity of the object. If, on the other hand, it's proportional to v squared, then I solve again the same type of equation, except now I get vt squared is equal to mg over the drag coefficient, and I have to square root this bottom equation here in order to get the terminal velocity. So in one case, let's think about this from the point of view of behavior. In the first case, in the case of the velocity, the resistive force proportional to the velocity, then the velocity is going to be proportional to the mass. And you should get a straight line with slope g over b. Okay? In the event that it's proportional to v squared, then I am going to get the velocity is going to be dependent on the square root of m with coefficient square root g over c. So I'm going to use coffee filters, so let me bring my regular screen up. And there we go. So here you see me. We're going to use the Mr. Coffee filters, and I have 5 of them. And I'm going to do this demonstration for 5 different masses. So I'm going to tack on a coffee filter each time I do a run. And as you can see here on my screen, I have the position and velocity for my motion detector, and my motion detector is up here, and it is ticking and ready to go. So I'm going to start my experiment. So I'm going to take one single coffee filter. I'll hold it up to the detector. I'm going to zero the motion detector before I drop. So now it is at 0, and I'm going to let the coffee filter fall. Now you can see that there's a little drift out, and the velocity actually humps up right about here. So we can think that the velocity is going to be constant right about here in our position versus time graph. Okay, so I'm going to store this run, and I'll maybe make it a little bigger so we can see what's going on. Here's the linear part. Here's the part we're going to analyze. Okay, as you can see here, the velocity is actually growing a little bit here. And part of that growth, you can see the little humps here are coming from the fact that the coffee filter is drifting a little bit. So it drifts in and out of the sonic beam. So now I'm going to grab 2 coffee filters now, and let's go ahead and now zero it again. And let's go ahead and do data. You can see that the curve is getting steeper as it goes. You can also see that there's a little bit of constant here. There's also that hump right here in the velocity versus time curve where the filters may have drifted out. That is a little tricky because we have air currents in the room, and that's going to be tough to beat. So now let's go ahead and store that run, and I'm going to continue on. Just a note, because of air currents and things like this, there might be a little bit of drift in the lab, and actually consider doing the lab. I would actually have 3 trials for each coffee filter. So there's 1 coffee filter, 3 trials for each every time I increment the coffee filters up. And that way I can actually get a good statistical average for the velocity. But to save time on the recording, I'm going to just leave it as at 1. 1 trial for each mass. So now let's go ahead and bring up another. We've got it ready to go. This is 3 filters. And 4 filters. So I'll store that. Store. That's a little bit better. And then the last one. So I'll save this run. And now I'll do the last one with 5 filters. Okay. So with that done, let's analyze the data. Okay. For each of these runs, I need to determine the slope where the velocity is pretty much constant. You'll notice that the motion detector itself is a height of 0.73 meters I tried to get it as high as I could, so that we could actually get a reasonable behavior of air resistance, but we're doing okay with what we have. So let's go ahead and I'll analyze. I'll start by hiding the other data sets and just going for the slope of the position versus time curve. Okay, so here's run one. And I'm thinking that for the most part, this becomes linear right about here. So let's do a linear fit. And I'll do this for each of these runs. So 1.25. Again, linear right about here. 1.57. So I'm going to pull these all the way over so we can get a good clear view. For this one, it looks like it's pretty much linear here. So I'll do the analyze at that point. Now notice that the velocity increases with the number of mass. This is kind of what we expected to happen. I don't know exactly how it increased, but I do know that it has increased linearly, or it has been increasing overall. We'll have to analyze that to get a better sense of what's going on. So let me bring up one more. Here's run 4, and I'll take this portion right about here. .65, so it's doing what we expect it to do, except for run 4. Run 4 looks like it dipped down a little bit. Maybe that is because we did not pick the right interval. Let's check that out. It looks like our interval is just fine for run 4. I'm going to drag that over there. Okay, that's as good as it's going to get. And then let's get run 5 up. So there's run 5. I'll select this region right here. So run 5 is this. So here's my data. So now that we have the data up, I am going to copy this and I'm going to get into that sheet that I'm going to share with you guys on Teams so that you can actually see this data for yourself. And I'll bring up my Mathematica. So there's my notes on drag. So now that I've got the theory, each filter weighs 0.93 grams in this experiment. So I'll paste my graph into Mathematica. There it is. And now I'm going to create a table. And the table is going to have 6 rows and 2 columns. So, okay, let's do new. And I want 6 and 2 columns. And we'll click OK. So the top is going to be the headers. That's going to be the mass. And grams. This guy is going to be the velocity in meters per second. Let me do one more row, one more column. And this is going to be VT squared. And of course we put the units in. All right, so there we go. So the mass, one coffee filter, I'm just going to use one coffee filter, just use 1, 2, 3, 4, 5. The terminal velocity for run 1 was 1.253. I'm just going to use 3 digits, 1.25. And that wasn't what it was supposed to do, okay. 2.5. There we go. And this 2.5 quantity squared. The next one, 2. I don't know whether this is going to be proportional to the velocity or the velocity squared. So I'm going to have to model that. So this one is 1.57 here. Okay, I'm just going to enter this stuff in. So just give me a second while I do that. Run 3 has 1.74, 1.75, I want to say, rounding up. Four, 1.64. This one I'm a little suspicious about. It's not behaving the way it should. And that is par for the course with any experiment. You're always going to have something that looks a little funky. And then this last one is going to be 1.86. So there's 5. 0.86. Okay. So there you have it. I'm just going to adjust my table so that I get something that makes sense when I execute it. And I have something freak out on me. Mathematica is a little touchy about things, so it can freak out, and I don't want it to. So here we go. Here is our data, and I will put it in table form. There we go. So there's our data. Now the question is, how are we going to analyze this? First of all, I can turn my first column, knowing that each coffee filter weighs 0.93 grams. Almost done. So now, redo. I'll display it as a table again. And here you have it. So I'll get rid of this. There we go. and I am going to call this my data. There we go. Okay. So here's my data. And in order to make a decision as to whether or not the resistive force is dependent upon the velocity or the square of the velocity, what I am going to do is I am going to make a plot of each of these versus the mass. Now, in the event that it's proportional to the square of the velocity, then what we should get a straight line in both cases. But with the other one, with the vt squared, the slope will be different than that of the first one. So let's go ahead and do this. So if I do this, list, sorry for the Mathematica commands, folks, but oh, let's see. Let me just go ahead and copy and paste this. There was a brief intermission in the recording while I actually set up the data for analysis. So I didn't want to waste your time watching me copy and paste a bunch of stuff. The big thing here is, number one, I set up, and I'll just highlight this. No, not in that color, for heaven's sakes. I set up a set of objects in my program for analysis. Data VT is the mass versus velocity data. And I actually did what is called a linear fit. Now that's a standard technique in most laboratory exercises. If you decide to carry on in physics or in engineering, you wind up having to do the same thing. It's always a good thing to learn this by hand, but this is not the time or the place to do that. So I set up a function which is the linear fit of the data versus to get a function out of it, to figure out the dependence of the data on the mass of the filters. And so the next thing I did here, so that's what this is. And we're going to test the correlation in just a few minutes, because that's what's going to tell us whether or not we're dealing with the resistance proportional to the velocity, or the resistance proportional to velocity squared. So here's my fit for velocity versus mass, or velocity versus mass in this second plot. And you can see what the data looks like for this particular plot. And I'll just label it plot label to velocity versus mass. So there's my velocity versus mass. Now, data VT2, this one here, is the data. So I'll put this, no, I'm going to highlight this in light blue. So there's data VT2. What this is the mass versus the square of the velocity. And you can see that I've also created a function for that. We're going to test the correlation in just a moment. So here's my background color, light blue, and I'll just create the function right now. Fit2 of mass. Okay, I don't want you to get too distracted with the coding, and I apologize for doing this live, but I figured it's worth seeing for the sake of argument. So there's Fit2. Here's the plot of the mass versus the velocity squared. So let me label that plot. So here's my plot. Okay, so the question is, which one gives you better correlation? This guy or this guy? If we were to make a plot of the line going through here, it would look better than the line going through here. Okay, there's more of a correlation. Now, I'm going to test that in just a moment using a function in Mathematica called correlation. Basically, what that does is it compares two pieces of data to see how well they correlate. Do you remember what correlation means? If you don't, I'm going to answer that question. Correlation means how good is the fit of the model. In other words, does this accurately represent what's going on in the situation, or is it loose? Remember that correlation of 1 means that it is exact. Correlation of 0 means there's no relationship between the data at all. And so I'm going to go ahead and do this now. And I'm going to correlate the mass and the velocity, and then the mass and the velocity squared. So correlation. So if I do that, I get about 88%. Let's take a look at data VT squared. Let's take a look at my second set, this guy here. .1 versus 88.89. So this is a percentage. The correlation between the velocity squared and the mass is much velocity squared and the mass is much higher than the correlation between the velocity and the mass. So what we can conclude is that the velocity, the resistance, is proportional to the square of the velocity. This seems like a little bit of a strange business, but again, when you're looking at a physics lab result, you're not looking at a single run. So I would say that part of what happened with this is the fact that we only did one run versus 3. So if you were to do 3 trials for each mass and then take that data and then do the correlation, you would actually find that the correlation data V2 is actually going to still beat out correlation VT because it should be about 95% versus 80% for VT. Okay, so this is drag, and as you can see, the object reaches a terminal velocity. Again, let me summarize. We use Newton's second law to generate the equations. Once we do that, we get we're going to look for the terminal velocity, which is the case where the resistance is balancing out the weight. We had two models, that the air resistance is proportional to linearly proportional to the velocity, or that the air resistance is proportional to the square of the velocity. We could look at the ideas presented in the text. They basically say for an extended object, you should get a air resistance that is proportional to the square of the velocity, not linearly. And as a matter of fact, the case of linear is when the radius of the object is much, much smaller than 1. So this is drag, and again, it's a resistive force. It acts against motion. So if the filter is falling downward, the air resistance is acting upward, and it actually buoys the object up. So hopefully this lab will make some sense to you. Here's my data. I will actually put this into PDF form so that I can share it with you, and you'll see this on Teams.